Record. Okay. Let's do a little bit of review, but I also left you with a problem to try last day. Wait. Put it at the bottom, I think. Try this for Monday. I'm going to grab this one while I can. Copy. Or while I'm here, rather. But let's do just a smidge of review. We introduced kind of the steps of hypothesis testing. Hypothesis testing is when we want to prove something. Hypothesis testing, which I'll abbreviate HT. And this is when we need to prove something. Kind of the formal way of proving a significant difference between two groups, for example, is what we'll pretty quickly move into. But really, kind of anything that starts with, is there evidence, is going to be a hypothesis test. Okay? And for any hypothesis test, what's really nice is once you have these steps kind of memorized or internalized, then they apply to any hypothesis test. So some things are going to change inside kind of the calculations that you do, but the general steps stay the same. So let's review those. Step one is to state your hypotheses. We've only talked about one type of problem. So the type of problem that we've introduced is one sample proportion. We have one sample of categorical data, and I have some proportion that I want to compare to some number. And so because I just have the one sample, so I can't compare it to another sample, because then I would need to have two samples, which we will introduce next, right? But for now, we've just got one sample, and I want to compare it to some number. And so what that's going to look like is you've got your null hypothesis, which is a statement, and it has to be a statement about the population. Now, because we have categorical data, the population parameter is the population proportion in this case. And we want to know, how does it compare to some value P naught? Okay. And I'll say where P naught is the value, it's a proportion, but I don't want to bog you down with that because there's so many proportions here, right? So it's the value, in this case of proportion, we want to compare the sample proportion to. We want to compare the sample proportion to. Okay. So if I want to know if more than 50% of people voted for some candidate, first thing I have to do is I have to assume that the proportion of people who voted for this candidate is equal to 50%. Until I have proof otherwise to say, that's if it was centered on 0.5, what I saw is highly unlikely. And so that gives me evidence to reject H naught. And so we always offer an alternative, the alternative hypothesis. Oh, and I meant to ask Allison, if you use H1 or HA, it can be flexible. Sometimes we use a lowercase a. I like a capital A, because my lowercase a tends to look like a 0, so that's bad. Then I have 2 zeros there. But my alternative is going to be P is not equal to P naught. We introduced this idea that, okay, we could have not equal to, which is a two-sided test, right? I don't care which direction. I just want to know if there's a difference. You could have less than, right? Did less than 50% of the population vote for this candidate, right? Or you could have more than. For us, even if we feel like we should be testing more than, I'm going to encourage you to just use the not equal to. It's going to be our default. Okay. And the reason for that is because sometimes if we want to know, oh, put some quotes on there. If we want to know if more than 50% voted for this candidate, so then we're only looking at one tail, which is fine. But then we kind of ignore the situation where our sample proportion is significantly less than 0.5, right? And that's bad. And so so the default is going to be this not equal to. Okay. And so, right, this sign determines which area in the tail we're interested in, right? Because later on, we're going to use the probability of seeing something as extreme or more extreme to determine if we can reject H naught or not. Here, so stating the hypotheses is the first step, arguably the hardest because you have to decide what type of question you have, right? And figure out what P naught is from the question. But after that, you're kind of on rails. We should check the conditions here, but I didn't introduce them last day. Sure. Check the conditions for the central limit theorem. In order for the central limit theorem to apply, we have these conditions. Now, the reason I'm kind of doing them in green is because I'm not super concerned about them. They take up a lot of brain space. And so they're always going to check out. And so just have a general idea of what the conditions are for a hypothesis test. And so the first one, or I guess there's the first part is the independence condition. Okay. This is going to be the same as for a confidence interval. The independence condition has two parts, but one main one. I'll just write randomly sampled. If our observations were randomly sampled, then we can assume that those observations are independent of each other. Not necessarily true, but we're allowed to assume that if we've randomly sampled. Okay, so that's one of the things that you're going to check. And that's going to be your go-to assumption, right, that you have to check. So this is the only one that I really care about. Right. Were these observations randomly sampled? The second one, which I'm going to say is optional, is the n less than 10% of the population condition. Now, I mention this because it's likely in wet, especially that you might have a small population. I don't know, but I imagine that there would be. And so then what you want to be careful about is that you don't sample too much of the population, which is kind of intuitive or counterintuitive rather. Because we know, okay, large samples are good, large samples are good, but then if we've sampled too much of the population, more than 10% of the population, then we start to introduce non-independence. Okay? That one's optional, but just something to keep in mind, right? As long as you've randomly sampled, then you're good. Okay? Those are the same as for a confidence interval, so I'll make a note here. Same as for a confidence interval. The normality condition or the sample size condition, whichever you'd like to call it. For a confidence interval, we had to have at least 10 observed successes and at least 10 observed failures. Now, for a hypothesis test, it's just slightly different because now I have this hypothesized proportion that I'm trying to capture. And so now I have to have at least 10 expected or hypothesized successes. Expected or hypothesized successes. How you're going to check that is by taking your n, your sample size n, times your p naught, your hypothesized proportion, and just making sure that it's greater than or equal to 10. Right? So just a slight difference. So here. And then on the flip side, we also need at least 10 failures. At least 10 expected or hypothesized failures. N times Q naught has to be greater than or equal to 10. I should make a note. This was not introduced last day. This is the first time we're seeing it. It's part of the review, I guess, but I'm sneaking it in there. So, sorry. Then we're ready for step 2. Once we've checked those conditions, they'll always check out. Or what do we have to say? We have to say, I assume these conditions are met, right? And so, right, either way, you're going to proceed to step 2, which I call do the test. Just kind of informal, but it makes me think of do the do, kind of fun, but calculate the test statistic doesn't really have that same ring to it. But technically that's what we're doing. I'm going to put it on, move it up just a smidge. So what we want to do is we want to see how far is my sample proportion from my hypothesized proportion, right? And so kind of to visualize it here, right? I've got my hypothesized center, and then I've got my, maybe my p hat is up here, my sample proportion is up here, and I want to figure out how far is this thing from p naught, right? If it's not very far from p naught, that's, well, then we can say that they're basically the same, right? The null hypothesis stands. If they're far enough away from each other, then we can say, okay, then I have evidence against H naught, which says that, hey, the center is P naught, right? If the sample that I've collected is far enough away, then I can say, that's evidence against it being centered on P naught. It's more likely that it's centered on something else. It's possible, but it's more likely to be centered on something else. So how can we do that? Well, we can calculate a Z, which is P hat minus P naught, right? Take that distance, but then we need to figure out, well, that distance in terms of the standard error. Now, the standard error used to be the square root of P hat Q hat over N, but now, because I have a hypothesized population proportion, we're going to use that instead. And so over the square root of P naught Q naught over N. And just as a reminder, this is the standard error for the hypothesized population. And that's the one we want to use. Okay. Then we're ready for step 3, right? We could try talking in terms of Zs, right? You find a Z, now Z tells you how many standard errors for the hypothesized population you are away from the hypothesized center. That's really boggy and hard to communicate, right? And so what we do is we take it one step further and we talk in terms of probabilities, right? In fact, we talk about the probability of seeing something as extreme or more extreme, and that's the p-value. So step 3 is find the p-value, where the p-value, just as a reminder, is the probability of seeing something as extreme or more extreme, making this the area in the tail, right? A probability is an area under the curve, and something as extreme or more extreme makes it the tail area. As extreme or more extreme than what we saw in our sample, assuming the null hypothesis is true, right? The null hypothesis says, hey, here's my center P naught, but then we find evidence against it potentially. So in our sample, assuming H naught is true, we're going to use software. Oh, that's what I have found a way. Could probably download Excel on my iPad. I just couldn't remember my Apple ID password. So we're going to use numbers. That's okay. They're the same. Right, and so here, use software to find the area. And here I'm going to say corresponding to the alternative hypothesis. Right? Depending on what the alternative hypothesis is, you might have P is less than P naught. Well, then if you want to prove that it's less than P naught, right, centered on P naught here, then this area is the p-value, right, from P hat. You better hope that your P hat is less than P naught. Otherwise, it's hard to use that to prove that it's less than, significantly less than P naught. And so this is your p-value. Or let me just copy this whole thing. Copy, paste, and paste 3 times over. It's going to change as the sign, right? And I guess this. Dink, 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 dink. If I'm hypothesizing, so if my alternative hypothesis is that P is greater than P naught, well, again, you better hope that your P hat is above P naught. Otherwise, it's hard to use it. Then the p-value is here. The tricky one that we introduced, right, and also our default, so it's worth getting to know, is the two-sided test, right? So now I'm interested in either tail. Our sample is only going to be in one of the tails. And so, for example, if our P hat is down here in the lower tail, I'm also concerned about something similar happening in the upper tail. So then both of these areas are the p-value. You take the area in the one tail and you multiply it by 2. Okay. Have an example, but this is all so important that it is worth doing all this review. But also it's been a while. So here, this p-value, you're going to find the area in one tail and multiply it by 2. By 2 to replicate the opposite tail. Right? Your sample is only going to be on one side, but you can find the area in the tail and then multiply it by 2. Then our final step is the conclusion. Uh-oh. That's not a good start to the week. I'm staring down the barrel of a lot of talking this week. So we said that if the p-value, right, if the area in the tail is small enough, right, which is really implying that our sample proportion is far away enough from p naught, then we have enough evidence to reject h naught. Okay, and so what we're going to say is that if the p-value is less than, right, if it's small enough, the alpha level, now the alpha level for us, I'm going to just use 0.05. You can adjust it and we'll talk about what adjusting it would do, but the default is going to be 0.05. And so if the p-value is less than the alpha level, which is the significance level, of 0.05 or 5% if you prefer, we have enough evidence to reject H naught. And then of course, the flip side of that would be if the p-value is not less than the alpha level, then we do not have enough evidence to reject H naught. And so I'll do the flip side. So is potentially not less than the alpha level, then we do not, oops, looks like one word. Do what? Do not. Yeah. Those are your only two options, right? It is either less than the alpha, less than 0.05, or it's not less than 0.05, but your conclusion has to be in terms of H naught. Why? Because we assumed that H naught was true. We did all our testing assuming it was true. And then now we're stating our conclusion in terms of H naught. And then, of course, your conclusion in terms of the question. Okay. Some lofty theory there. So let's do this. Let's, bless you, let's do this thing. Here we go. Oh, I copied over it, didn't I? Where is it? Copy. Come on. Here we are on Monday, trying it. Well, you probably tried it earlier. I guess I should ask if there's any questions before we actually do the problem together. Seeing none. Well, you know what to do. You can ask. All right. So it's referring to the same survey that we were talking about for the confidence interval. We're just talking about a different question on the survey. And so the same survey asked the 850 respondents. And so first thing I'm going to do is make a note here that N is 850. How comfortable they are with Facebook creating a list of categories for them. 41% of the respondents. Now here, right, if it's of the respondents, then this must be a sample proportion, right? In fact, P hat must be 0.41. Said that they are comfortable. Do these data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating a list of interest categories for them is different than 50%? So we have a sample proportion of 41% and or 0.41, and the value that we want to compare that to is 0.5. So here, this means that P naught is 0.50. And I want to know if it's different than 0.50. Okay. So here we go. Step one, state the hypotheses. State the hypotheses. This is not usually obvious, especially as you're first starting out, right? There's a couple of numbers here, but just keep track of which one came from the sample and which value you want to compare it to. It sounds obvious when I say it. It's going to be one of those things where you sit down to do your own problem and, oh, it was so obvious when she said it. But it takes practice. So our null hypothesis is that P is equal to P naught, but P naught in this case is going to be 0.50. Right? And so that goes here. How does the proportion compare to 0.50? You could do 0.5, but I think it looks weird. So I do 0.50. Our alternative hypothesis, usually the one that we are trying to prove, but we have to assume that it's centered on 0.5 until I have evidence otherwise. So I'm trying to prove that P is not equal to 0.5, right? That they're different from each other. Or different from 0.5. We're going to check the conditions. The conditions for the central limit theorem. The first one is independence. Now, here, it doesn't say that these respondents were randomly sampled. And I think in the original blurb, it says a representative sample. And so I'm going to say that we assume the sample was randomly selected. That's fine. It's more like, so the conditions or the assumptions, it might be more helpful to think of it as checking your assumptions or stating your assumptions. So randomly sampled, we assume the sample was randomly selected. The next one's optional, but why not? Oops. It's reasonable to say that a sample size of 850 is less than 10% of American Facebook users, right? And equal to 850 is less than 10% of American Facebook users. So there's no risk of non-independent observations, or at least not reasonably. So the independence condition is met. Now we move on to the normality condition. Normality, or the sample size, we need to have a large enough sample in order for that normal distribution to appear. So the sample size condition, first we need n times p naught, which is 850 times 0.5. Is it 425? That's greater than or equal to 10, so that checks out. Like I said, these things will always check out. It's just our job to remember to check them. Not in real life, though. What if you were doing this in real life and for some reason the condition wasn't met? Right? Well, let's think about how would it not be met. That would hinge on trying to detect a very, very unlikely thing, right? A very, very small proportion. Thinking about rare diseases, things like that, right? You'd have to increase your sample size a lot to be able to detect something very, very rare, right? And so that's when it wouldn't be met. Even if you've collected the largest sample size that you could afford and this condition wasn't met, what would you have to say? You'd have to include that in your report and say, unfortunately, our sample size is not large enough, but we're going to assume that the central limit theorem applies anyways. And so we're always just stating what we're assuming, state our assumptions. N is still 850 and 1 minus 0.5 is 0.5, which is still 425, which is still greater than or equal to 10. Therefore, the conditions for the central limit theorem are met, which means that we can assume a normal distribution, which is what we need to be able to calculate and use a Z to find probabilities. So that's important. Step 2. So if you did it on your own, then you wouldn't have those conditions being checked because I just introduced them today. Step 2, do the test. Z is p hat minus p naught over the square root of p naught q naught over n. Let's remind ourselves that p hat is 0.41, p naught is 0.50, q naught is also 0.50, 1 minus 0.5, and n is 850. Looks like we have all these components. So it's a matter of plug and chug. Now I would probably, if I was on a laptop, I would probably prefer to use Excel to do this calculation. I'm gonna try my best, but I'm gonna just write them out here first. So I'm gonna do 0.41 minus 0.50, right? How far is my sample proportion from my hypothesized proportion, taking into account the spread, which is going to be 0.50 times 0.50 divided by 850 and then square root it. This doesn't look like There. Okay, let's see. Where's my numbers? There. See, it was working, but not very good at using it. Okay. No. How can I delete this? Okay, sure. So I wanted to do, I'll do these incrementally. First, I'm going to find the standard error. That's going to be kind of a tricky one. Right, that's the square root of P naught Q naught over N. And so I'm just going to do that separately until we're comfortable with working with these things. And so I'm going to have the square root. Is there a square root on here? I want the squirt of, and then the numerator in brackets 0.5 times 0.5 and bracket divided by 850. And bracket should do it. Is that the same? Good. Let's see if I can zoom in here. So then my Z is going to be in the numerator. So equals, and I want in brackets 0.41 minus 0.50. Close that bracket and then divide by this standard error, which I'm going to reference the cell so I don't lose any decimal places. And then that should be good, return. So this Z tells me that, okay, 0.41 is 5.25 standard errors below the hypothesized proportion. That's really far away, right? In fact, we use 2. Any standard, anything more than 2 standard errors away is considered extreme, right? And so I'm going to copy this, or try to. Fine. Screenshot this. All my screenshots of on my iPad are very, very boring. There. So we have a Z that's really, really far away, right? 5.25-ish standard errors below the hypothesized center. And so now we're ready for step 3, which is find the p-value. The p-value is the area in the tail. And this is where we need to remind ourselves that, okay, Z is centered on 0. So let's draw it out. Right, Z is centered on 0. And we found a Z way down here at roughly negative 5.25. Right. That's just taking our sample proportion and standardizing it onto a curve that's centered on 0 instead, taking into account the standard errors. And so here, what we're going to find is this area in the tail. Right, this is the one-sided p-value. But we also remember that, okay, my alternative was actually that p is not equal to 0.5. So what I need to do is I need to take the area in one of the tails and then multiply it by 2, right, to say, well, I would be equally concerned if I saw this in the upper tail. And so how are we going to find the area under the curve? To find the area under the curve, we use the norm inverse command norm.s.inverse probably. So here, the one-sided p-value, oops, is going to be equals, to get us into the function. And let's see, norm inverse, norm S inverse, I think is the same one as the norm.s.inverse in Excel. Oh, we don't want the inverse. I don't want a Z. I want the p-value, so I want the norm S dist. Sorry about that. Norm dist, norm S dist to match Excel, hopefully. And then I want to give it the Z value, which is the one up above here. Turn. So I get this. Saved photos. Bring it in. I guess I should have done the two-sided already. So this is very, very, very small, which matches 5.25 being very far away, right? And so now we have this probability, the probability of seeing a sample proportion of 41%, if it was actually centered on 50%, well, it's this small, right? So trust your gut and say, well, that feels way too unlikely. Possible, right? There is some probability of that happening, but it's very, very, very small. So then we say, this is definitely less than 0.05. In fact, even when we multiply it by 2, right? So this here is the one-sided p-value. That's the area in the one tail. So now we're going to multiply it by 2. Turn. I wonder how I can show more. So the two-sided p-value is equal to this times 2. Turn. I'll highlight that. Take a screenshot. Oops. Notice also that I'm keeping the commands showing here, right? That's the same as the formula bar in Excel. It's just below instead of above. That's the only difference. And so that's why I'm keeping them in my screenshot. So therefore, the two-sided p-value is 0.12345, 6 zeros, 1, 2, 3, 4, 5, 6, 1, 5, 4. Couldn't squeeze another one on there. Approximately, I guess, but that's close enough, right? And so now we can use this to draw our conclusion, right? If the p-value is small enough, which I say it is, why? Because it's less than 0.05, it's less than 5%, right? That's itty bitty. So now step 3, I'll put it on, or step 4 rather, our conclusion. We're gonna say, so we use the p-value that we found as part of our argument. Since the p-value of, or the two-sided p-value really show off everything that we have covered, is approximately 0.000000154. Let's start there. Since the two-sided p-value of 0.123456154 is less than alpha equal to 0.05, we have enough evidence to reject H naught, right? If the p-value is small enough, then we can reject H naught. Is less than 0.05, we have enough evidence to reject H naught. If we're rejecting H naught, we should probably say in favor of what? In favor of the alternative hypothesis. The alternative hypothesis was that the population is not centered on 0.5, it's centered on something different. And so that's more likely in favor of HA. Now, we need to say what that means in terms of the actual question. And so usually what I encourage you to do is I just want you to reword the question as an answer, right? And so I'm going to go back to the question. And I'm going to snag this last part. Copy. Paste as an image. Good. And then what I'm going to do is I'm going to edit this. Do these data provide convincing evidence that the proportion of American Facebook users are comfortable, I guess, who are comfortable with Facebook creating a list of interest categories for them is different than 50%? These, just as a statement, these data provide convincing evidence that the proportion of American Facebook users, I'll throw in a who here just for clarity, who are comfortable with Facebook creating a list of interest categories for them is different than 0.5 or 50%, no question mark, period. Sounds fancy, but I'm going to set up the question so that you can just reword it as an answer, right? But you do have to answer the question. So notice, right, we've got these three distinct parts of the conclusion, and you always have to do all three parts. I'll see if I can close this up here. There. So the first part of the conclusion, let's do it in purple, is that you're going to compare, right? The first part of the conclusion is compare the p-value to the alpha level. Is it less than or is it not less than? Compare the p-value to the alpha level. Second part of the conclusion is your conclusion in terms of H naught. Do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? The conclusion in terms of H naught, right? Because we did all our testing assuming H naught was true. So now you either reject it or fail to reject it. It's really important that you don't say that you accept a hypothesis, okay? Because accepting a hypothesis means that the probability of this happening is 0, and that's never going to be the case. Thinking about how the tails just go to infinity and negative infinity, right? So there's always a probability of it happening. And so here we never accept a hypothesis, whether it's the null hypothesis or the alternative hypothesis, right? I will take marks off if I see I accept this hypothesis. What's the big deal, Emily? It's no big deal. It is a big deal, right? Because there's always a p-value probability of being wrong, right? It's very, very, very small, but there's a chance that you're wrong, and you have to recognize that. In fact, using an alpha level of 0.05, you started out saying, I'm okay with being wrong 5% of the time, right? And so you've already set out saying, oh, there's a chance I'm wrong. Oh, well, right? And there's always a chance that we're wrong because we're using sample information. But so we never accept a hypothesis because there is always a p-value probability that we are wrong, especially if we're rejecting H naught. Okay. Okay. So although it's tempting, I don't want to see it. Okay. So you either have enough evidence to reject H naught or you don't. And finally, of course, the conclusion in terms of the question, what does rejecting H naught mean in terms of the question? So always 3 parts. Usually your conclusion is worth 3 marks, right? Because it has all these components. I'm not too concerned about you being able to do the math and stuff like that. So that's only 1 mark. So usually a hypothesis testing question is about 7 marks. So 3 out of 7 marks for your conclusion. It's a heavy hitter, right? Stating your conclusions, stating your hypothesis or hypotheses is, I don't know, 2 marks usually. I'm not including checking the conditions because usually I'll just say, assume the conditions are met, right? I think maybe on the quiz, and we'll have a quiz this week, I guess. I'll open it on Friday and I'll keep it open until Sunday night, just so you have more time to do it. It'll be a timed quiz, and it'll be on just this theory, right? Because I realized I'm kind of slipping behind on the quizzes. Should probably throw a quiz in there. Maybe I'll put that at the top of our notes. Quiz number 2. How's that for sneaky? Quiz number 2 on Friday / the weekend. You'll have time to work on it, right? Once you open it, it'll be a timed quiz, but you'll have a choice. Usually it's about 20, kind of 20 multiple choice. Yeah, I'm going to focus on hypothesis testing because there's a lot of ground to cover, and it'll be theory. So. Well, less theory, not Excel. No, because I don't like making you do Excel under pressure. Yeah, I know. Because yeah, so. Yeah, so I didn't like that. So changing gears. So it'll be a purely theory, and then you've got other assignments. I'll give you an assignment that's not necessary. You don't have to use Excel for it, but just to give you kind of more practice with confidence intervals and hypothesis testing as well. But it'll be theory. And it's open book. So you can, right? It's timed, so that's stressful, but you can do it. I guess that means I have to make it. I need to stop assigning stuff so I don't have to make stuff anymore. Right? Yeah, we'll just call it quits here. Just come hang out. It's good, right? Yeah, we'll take spring break. Yeah. I'll be in Mexico so fast. With everyone else. Okay, so there it is. Like I said, so that's kind of the end of that question. Hypothesis testing questions are very involved, right? They take a lot of work. And so there's a lot of ins and outs, right? But so when we do a hypothesis test, right, like I was saying and harping on, there's always a chance that we are wrong, right? That our decision is wrong, right? We use probabilities to decide what to do, right? But there's always a chance that we're wrong, right? And so when we conduct a hypothesis test, there is always a probability that we're wrong. Oops. In fact, there are two ways that we could be wrong, right? Now, the problem is we don't know what the truth is, and that's okay, right? We don't know if the population is centered on 0.5, if the population proportion is 0.5. We know that if I had the entire population of American Facebook users, I could calculate a population proportion, but we don't need to do that, right? Because we can assign probabilities to this sample happening. So 850, that's a lot easier to collect and work with, right? And so there are kind of two scenarios here. Usually we do kind of the truth, right? The population truth, which is unknown to us, but it exists, right? That's the tricky part, is it exists, right? But we don't know what it is, and that's okay. Let me get myself a little bit more room. And also our decision, right? Our decision based off of the p-value. What were our two decisions? I can either reject H naught or fail to reject H naught. H naught might be true or it might not be true. So H naught is true, or H naught, or let's say HA is true. That we don't know. Right? And so we've got these kind of four options for our outcomes. If I've rejected H naught, but H naught is true, that's a decision error, right? I've made a mistake. Right? So here, this is a decision error. Oops. I rejected it when I shouldn't have. And so we call this a type 1 error. That's what it's called. You've rejected H naught when you shouldn't have. And so the probability of making a type 1 error is the alpha level, right? I'm okay with making a type 1 error 5% of the time. Yeah. If I fail to reject H naught, which means that I'm just going to keep it, right? And H naught is true, well, that's a good thing. That's not a decision error, right? That's fine. Yeah. What if I've rejected H naught? Whoops. And the alternative is true. Well, that's also fine. Right? What if I fail to reject H naught when it's false? So H naught is false or HA is true. They're complementary that way. That's also a decision error. And we call it a type 2 error. I'll do Roman numerals. Yeah. The probability of making a type 1 error is the alpha level. And so that's where we're going to focus our time. Put it on a new page here. The probability of making a type 1 error is the alpha level. So that's a default of 0.05, right? So we start with 5%. Okay? Now, if the cost of making this mistake of rejecting H naught when H naught is true, right, is very, very expensive, then what would you want to do? You'd want to decrease your alpha level, right? You want to make it harder to reject H naught. Okay. And so some examples of kind of costly type 1 errors would be something like, well, if you reject H naught and your recommendation is, yeah, replace all your machines in your entire lab, and that's going to cost you a fortune, when it's not necessarily true, that's expensive, right? So it can be financially expensive. It can be kind of expensive. It can, I want to say emotionally, maybe not emotionally in a business sense, but it can just be taxing on the population, all these things, right? So there are costs associated with making these mistakes. And so if the cost is financial or time or even emotional or kind of population cost, so if the cost of making a type 1 error is high, we decrease the alpha level, right? We can decrease it maybe to 0.01, right? Making it harder, which makes it harder to reject H naught, right? If it's harder to reject H naught, then you have more evidence. You have to have strong evidence, right? And so especially if you're doing kind of vaccination studies, you're probably not okay with a 5% level. You should probably decrease it to 1%, right? Or maybe even something smaller, but 0.01 is usually good, right? There's one example that I think of, or a problem that I always think of, and it's the diameter of catheters. Now, you don't want to be kind of willy-nilly on the diameter. Oh, well, that one was a little bit bigger. Oh, well, that one was a little bit smaller. So then you want to be really sure. So then you use 0.01, for example, right? And so it depends on the cost. Sometimes maybe you have a small sample size and you're okay. Then you can increase the alpha level to 0.1, but the default is 0.05. Now, So the type 1 error, the probability of making a type 1 error, that's the one we have more control over, right? We can control it by setting our alpha level. The type 2 error is when I fail to reject H0 when I should have rejected it, right? And so I don't have very much control over that. The only way that I can decrease the probability of a type 2 error is by increasing my sample size. So the only way, I guess I shouldn't say only way, because I'm sure there's another way, but for us, let's say the only way to decrease the probability of a type 2 error is by increasing the sample size. So we don't have very much control over the type 2 error. It kind of is what it is, right? But I guess I should summarize in words. Probably should have done this before talking about the probabilities of them. Type 1 error, type 1 error is when we reject H0 when it shouldn't be rejected. When it shouldn't be rejected. The classic example is kind of in a courtroom situation, right? And so the null hypothesis is that this person, I don't know, who's on trial, I guess, is innocent, right? We have to assume that they're innocent until we have proof otherwise, right? And so then if I say that they're not innocent when they are in fact innocent, that's a type 1 error. Now, the reason I don't write that one down is because I always found it kind of confusing to me personally. So, but if you look up type 1 error, type 2 errors, that's going to be the first example that pops up, is this courtroom situation, right? But for some reason, I can't seem to wrap my head around it easily, which kind of defeats the purpose of an example. And so a type 2 error, or I should say, it took me a long time to wrap my head around it. That's what I should say. So a type 2 error is when we do not reject H0, but it should be rejected. Should be rejected. In the courtroom situation, that would be the same as saying, well, yeah, this person is innocent when they are not, right? And then the argument is, well, we shouldn't be sending innocent people to jail, right? And so that's worse than letting guilty people walk free. That part always kind of bothered me as well. But anyways, enough of my troubles with that example. So hypothesis testing, did an example, talked about decision errors, and that's good for today, I think. If you have any questions, let me know. Otherwise, see you on Wednesday. See ya.